with the chapter light reflection and refraction. So we finished reflection, the spherical mirrors, and we were about to finish the refraction. And now we are going to do the spherical lenses. Spherical lenses, in this we will do the ray diagrams, image formation, uses of spherical lenses, then lens formula, magnification and power of lens. Power of lens is a additional topic to what we just studied in spherical mirrors. This is very similar to the spherical mirrors, just an addition is power of lens. So we'll quickly move on to the what is spherical lenses. Spherical lenses, like the spherical mirrors, there are two types of spherical lenses, convex and concave lenses. There we would have studied concave and convex. But then please remember that the curved out will be the convex lens and the curved in will be the concave lens. So we'll see the differences. This is a converging lens because it is curved out, and the rays parallel to the principal axis will converge at a point. That's a diverging lens because it diverges. All the rays will come out of the focus. Okay. This is curved out, that is curved in. And there is one more difference between these two. Here, the edges of the convex lenses are thinner. Edges are thinner, but the center part of this convex lenses are thicker. The opposite will be the edges of this concave lenses will be thicker than the center. It will be thinner. Okay. So now, again, the basic terminologies of the lenses. We saw the basic terminologies for the mirrors, right? So we'll see the basic terminologies. What would be this? The center point? It was pole there. It is optic center here. Optic center O. Optic center O is the center of the lens. Okay. What would be this point? Yeah, the center of curvature, right? So we saw center of curvature there, C. But then here, what would be this? This is F1. Okay, there are two focal lengths, two focus that we have in lenses because there are two refracting mediums. Okay, so this side it will be F1 and this will be F2. So this would be C is equal to 2F1 and this point would be 2F2. Same, the the principal focus is the point where all the rays converge at the focus, that is the principal focus, and the length between the distance between the optic and optic center and the focus one will be F, the focal length. The same length will be, the same distance will be the distance between C and F1 or 2F1 and F1. So we use 2F1 and 2F2 here for the lenses instead of R and C. Okay. And instead of pole, we say this as optic center. We know this black line that is passing through this lens is called as, or the passing through the optic center is called as principal axis. Good. So principal axis, and then the aperture we saw it, right? Aperture will be the amount of light entering between M and N. Yeah. So what did we see? Optic center O, F1, F2, focus, 2F1, 2F2, center of curvature. Good. And the aperture, M and N would be the aperture, the amount of light going through the refractive material. Okay. So with this, we'll go to the image formation. Very easy, very similar to the spherical lenses. Correct. So convex lenses, it will be 6 cases. And concave lenses, it will be 2 cases. So we'll see the first one. The ray diagrams here, the rules will be the same, but whenever the rays pass through the optic center, there will be no deviation. Okay. And whenever the rays are parallel to the principal axis, they converge at focus, and after passing through the focus, they will go parallel to the principal axis. Very good. That is all. Only 3 cases. Okay. So the first one, we'll see the first one. All the rays are parallel. My object is at good, at infinity. Very nice. You remember. Good. So when the object is at infinity, we'll see all the rays parallel to the principal axis, and they meet at F2. Okay. So F2, at F2 will be my image formed. What will be the size? Yes, it is point sized. Point sized. So nature, real and inverted. Good. Real and inverted. Now the opposite of this. We'll keep the object at F1. Good. We'll keep the object at F1. Where will be the image? Image will be formed at infinity. Why? There is one ray parallel to the principal axis and goes through F2. And the other ray, which is going through the optic center, it will be undeviated. There will be no refraction. So it will also be parallel to the ray passing through the F2. So it will be joining at infinity. Okay. What will be the size of the image? It will be good, enlarged. Enlarged and real and inverted. Okay, good. These cases are very easy, because when you study the spherical mirrors, if you have studied properly, and this would be very easy. It's the same of that, but then the terminologies change. Okay, make sure you study the lenses and mirrors properly without confusing. Okay, moving on to the third one. My object is at beyond F2. Good. Beyond F2. 2F2 or 2F1. Sorry. So beyond 2F1. Now my object, there is one ray passing through O optic center, and one ray is parallel, which is passing through the F2 on the other side. So the image will be formed between F2 and 2F2. Good. So size, what's the size? Diminished. Diminished. Okay. Nature, it is inverted. So real and inverted. Good. The opposite again. So my object is between 2F1 and F1 itself. Okay. So my image will be beyond 2F2. Image will be beyond 2F2. And the size, it's enlarged. Good. Enlarged. And again, it will be real and inverted. Opposite of case 3 and case 4. Okay. So the next 2 cases, which are very unique again. So my object is at 2F1, right? My object is at 2F1. Where is my image? Yes, it will be at 2F2. The size? Same size. Good. No change in the size. There, what was the position? In spherical mirrors, what was the position of 2F1 and 2F2? C. It was C. Here it is real and inverted. But if you see in spherical mirror, the image was just behind, just the opposite of the object, just down the object. Okay. So, yeah. So here, if you see, it is in the opposite side of the object. Okay. Next one. When I take little closer, my object is between O and F1, optic center and F1, right? So my image will be behind the object itself. So you can write behind the object, or it will be between two F1 and F1. Okay, two F1 and F1. Okay. So the image will be highly enlarged. It will be real or inverted or virtual and erect. It is just behind the object itself. So it will be virtual and erect. Good. Virtual and erect. So are you okay with this 6 cases? Convex lens at infinity at F2, it will be point size, real and inverted. The object at F1 will create an image at infinity. It will be enlarged, real and inverted again. The object will be beyond F2, F1. The image will be between two F2 and F2, the other side. So it will be diminished, real and inverted again. If you keep the object between two F1 and F1, the image will be beyond two F2 and the image will be enlarged, real and inverted. And the last two cases are very unique, as I told you, for the spherical mirrors as well. If you keep the object at 2F1, the image will be also at 2F2, 2F2, not 2F1. Okay, 2F2. And the image will be same size, real and inverted. When you keep the object between the optic center and F1, that is, you take the object little closer to the lens. When you keep that in the between the object, optic center and the focus 1, the F1, you'll get the image between two F1 and F1 on the same side of the object, just same side of the object. And it will be enlarged, but that will be virtual and erect, right? So we'll move on to the concave lens. There are only two cases as I told you. Concave lens at infinity, object will be at F1. You have to retrace it. Object will be at F1. Okay. So this will be again point sized. And this will be virtual and erect. Good. It will be virtual and erect. Good. It will be virtual and erect. When you see the second case, it is between infinity and the optic center, right? Between infinity and optic center here. Wherever you keep between infinity and optic center, you will definitely get the image between optic center and the focus 1, F1. How will what will be the size of the image? It will be diminished. And what about the nature? Virtual and erect. Good. So concave lenses will produce only virtual and erect images. Convex lenses produce real and inverted image, and the last case was the virtual and erect image. Good. So hope you're clear with this image formation of concave and convex lenses. We'll now see the uses of concave and convex lenses. These concave and convex lenses are used in correcting the vision of your eye. So it is usually the far-sightedness and the short-sightedness image, the defects. And we'll see in the next chapter which lens is used for which defects. So concave lenses are mostly used for our specs, glasses, and for the torch lights. Okay, torch lights to focus lights. Even your headlights will have this concave lenses. But in convex lenses, they are used in microscopes and for magnifying things. So when you use it in microscope and even in telescope, you can magnify things easily. So you can see an enlarged image as well. So these are the uses of concave and convex lenses. With this, we'll move on to the sign convention. Sign convention, I have taken a convex lens. Okay. So my 0, 0 in the graph, as I told you earlier in the sign convention of spherical mirrors, 0, 0 in the graph will coincide with here its optic center. Good. O. Okay, there it was pole. So now we, with all our cases, we have kept our object on the left side. Okay, so this is minus x plus x, y, and minus y. So now if you see, this will be my HO. So my HO will be image object height will be always object height HO is always positive. Okay. So my object distance we call it as U. Good. It will be always negative. Good. Good. Negative. Then my image distance, it will go positive and negative. It will be image distance V will be positive for real and inverted images. Positive because it goes there, right? In the other side. It will be for real and inverted images, and negative for virtual and erect images. Because virtual and erect images will be produced just in the side of the object itself. Okay. What about the focal length? Okay. So focal length, when we say about the focal length, we have two cases. We have to talk about two cases because it is convex and concave. When we saw the first case of convex lens, we saw all the rays are coming parallel this side and they all converge at F2. So F2 is on the plus x-axis. So focal length of convex lens will always be positive. Okay, it will always be positive. What about the concave lens? It was F1, right? It was F1. All the rays were diverging from F1. So it will be negative. Good. Focal length of convex lenses will always be positive and the focal length of concave lens will always be negative. Good. Okay. We have seen the image distance, image height we have to see. Image height, you can say from your spherical lenses itself. What will be the image height for real images? Image height will be negative. Negative for real images and positive for virtual images. Good. So image height will be negative for real images and positive for virtual images. Fine. Hope you're clear with this sign convention. We've seen the same thing in the spherical mirrors as well. Okay, there should be no confusion between the sign convention of the spherical mirrors and the sign convention of spherical lenses. Very easy. Okay. Lens formula and magnification. There we saw mirror formula and magnification. Lens formula is 1 by f is equal to 1 by v minus 1 by u. There it was 1 by v plus 1 by u. Okay. So f is the focal length. V is the image distance. And u is the object distance. Good. What about the magnification in your spherical mirrors? It was magnification is always the ratio of height of the object to the height of the image to the height of the object. Okay. And the relation between height of the image and height of the object to the object distance and image distance was minus u v by u there, but here it is simply v by u. Okay. Magnification is always hi by ho, and that will be equal to v by u. There it was minus v by u. Here for lenses it is only v by u. Okay. So The power of lens will be 1 by f. The power of lens will be the P equal to 1 by f. 1 by f is the reciprocal of the focal length. Power of lens is defined as the reciprocal of the focal length. It's the unit of this P. The power will be diopter. Diopter. Or you can simply write it as D or m power minus 1. So I can it's diopter D or m power minus 1. Okay, your focal length should always be in meters. When you are doing with the power of lens, it should always be in meters, not in centimeters. Okay, so I hope you're clear with the lens formula, magnification, power of lens, and your image formation. So we'll now move on to the problems. Yeah, the focal length of a thin lens is given by f equal to minus 10 centimeter. Is this a concave or a convex lens? F is minus 10 centimeter. Minus 10 centimeter. So your focus is in the negative x-axis. So is it a concave or a convex lens? It's a concave lens. It's a Good. It's a concave lens. Okay. When the focal length is negative, it's a concave lens. Good. The power of a lens used in the reading glass of a person is 1.5 diopter. Is this lens a concave or a convex? So your power is 1 by f, and that power is equal to plus 1.5 d. Okay, plus 1.5 d. I have to find my focal length, right? So my focal length will be 1 by 1.5. It will be plus again. So when my focal length is plus, okay, it is positive, what will be my lens? Is it a concave or a convex lens? My focal length is positive here. So is it a concave or a convex lens? It's a convex lens. Good. It's a convex lens. Because your convex lens has the focal length on the other side, 2f2 or 2f2 only. All the light rays parallel to the principal axis will converge. Okay. It's a convex lens. Good. Now, a 4 centimeter in size, the object 4 centimeter in size is placed at a distance 30 centimeter from a convex lens of focal length 20 centimeter. Find the position, nature, and the height of the image. Now, what is given? Just write the what are all given in your question. What is given? Object of 4 centimeter. So, HO is 4 centimeter. It is positive always. Done. At a distance of 30 centimeter from the convex lens. This object is placed in front of the convex lens. So, U will be minus 30 centimeter. Make sure it is, make sure your units are given properly and you write it properly when you write down for the given. And the focal length of the convex lens is 20 centimeter. So focal length of the convex lens is always positive or negative? Yes, it's positive. 20 centimeter. You have to find the position. Find V, HI and nature, right? Whether it is real or inverted, all those things. What is the connection to find V? You have U, the object distance, focal length, and you have to find the image. So, what will be the formula? 1 by F is equal to 1 by V minus 1 by U. Yeah. Now, just substitute 1 by 20 equal to 1 by V minus 1 by minus 30. Okay. So, this will be plus 1 by 20 equal to 1 by V plus 1 by 30. Yeah, 1 by V plus 1 by 30 when we have to find V. So I'll take my 30 to this side. So if I do that, 1 by V is equal to 1 by 20 minus 1 by 30. When I take the LCM of 20 and 30, I'll get 60. Good. It will be 60. What? 1 by 60 it will be. I have to take the LCM. 60 will be the LCM of this. So then we have to take the LCM for the fractions. We have to multiply. So I'll get here it is 3 20s are 60 and 2 20s are 60. 2 30s are 60. I'm sorry. So this will be 1 by 60. 1 by 60. So what will be my V? V is equal to plus 60 centimeter. Okay, I found out my V. I found out the first part. Done. It is plus 60 centimeters. So that means the image is on the other side. Okay, fine. Other side of the lens. Fine. Next, we have to find HI, right? HI. What is the relation between HI, HO, U, V? Yes, magnification. Magnification, HI by HO equal to V by U. When you do this, HI will be equal to V is 60 by U is minus 30. And what about your HO? It will be multiplied 4, right? 4. Yeah, it is 4. So when you do this, this will be 2 and there is a minus. So HI will be minus 8 centimeter. So when you have minus in the height of the image height, what does that mean? What is that indication? Is it a real inverted or virtual erect image? Yes, it is a real and inverted image. Now, the nature of image will be real and inverted. Yeah. So with this, I think I hope you're clear with this problem. So we'll move on to the next one. A 2 centimeter high object is placed 12 centimeter from a convex lens perpendicular to the principal axis. The lens forms a real image whose size is 1.5 centimeter. We have to find the power of the lens. Good. Okay, so what is given again? Given is HO is given. It is always positive. We can write plus 2 centimeters. Yeah. And U is given. U is minus 12 centimeter because it is convex lens, and U is always negative for either a convex lens or a concave lens. Then real image. You have, yes, a height of the image, which is real. So it will be negative 1.5 centimeter. Okay. So we have to find, indirectly, we have to find F, V, and then P. Am I right? Yeah. So with these, we can find V, HI by HO equal to V by U. So V is equal to HI by HO into U. So HI is 1.5 divided by 2 into minus 12. So 2 6 are positive. V will be positive. 6 into 6 15 is 90 and it is 1.5 here. So I take it as 9 plus 9 centimeter. Done. First part is done. I found the V part. Now I have VU. I have to find F. So 1 by F is equal to 1 by U, 1 by V minus 1 by U. Okay. So 1 by F is equal to 1 by 9 because it's plus 1 by 9 minus 1 by minus 12. So this will be 36, 4 plus 3, right? 4 plus 3. This will be 1 by F. So 1 by F is 7 by 36 and my F is 36 by 7 centimeter. Yeah, everything is in centimeter here. But to find power of lens, what should be the focal length unit? You know the focal length. You know the focal length should be meters or centimeters? Yes, it should be in meters. Okay. So to find the power of lens, the focal length should always be in meters. So when you have to change this meter to centimeter, centimeter to meter, what should you do? You should one centimeter is 1/100 meters. Okay. So you should divide 36 by 7 into 100. It will be 36 by 700 meters. Yeah. Okay. So what is the power of lens formula? P is equal to reciprocal of the focal length. Good. 1 by F. So 1 by 36 by 700. This will be 700 by 36. And power of lens will be around 19.44 diopter. Good. It will be 19.44 diopter. Are you clear? So with whatever is given in the form in the question, just write down whatever is given and then choose the correct formula with the relation and find one of the variables that is given to be found out, and then you can just build it on. Yeah. Okay. And I think this is the final question. We'll finish this, and an object is placed before a concave lens. It's a concave lens of focal length 12 centimeter. The size of the image formed by the lens is half the size of the object. Calculate the distance of the object from the lens. Okay, so focal length is given and it's a concave lens. So for concave lens, your focal length will be positive or negative? Negative. Good. It will be 12 centimeter. And the size of the image is formed by the lens is half the size of the object. Then I can say that HI is equal to half the size of the object, right? So size of the image of the formed by the lens is half the size of the object, right? So can I write HI by HO equal to V by U equal to 1/2? Half. The ratio is half. So can we say that U is equal to 2V? Yes, U is equal to 2V. We know F also. So what should be the formula? 1 by F. Good. 1 by F is equal to 1 by V minus 1 by U. In the place of U and F, please substitute the values. It will be focal length will be minus 12 equal to 1 by V minus what is U here from this? It is 2V. 1 by 2V. 2V will be the LCM. So minus 1 by 12 equal to 2V. Just multiply 2 here. 2 minus 1 minus it will be minus. Why minus? Because it is always negative. So this will be plus. So 1 by 12 equal to 3 by 2V. And V will be equal to 3 by 2 into, this will be minus 3 by 2 into 12. V is equal to minus 18 centimeter. So your object will be to find you have to find the distance of the object from the lens. So your object distance will be U is equal to minus 36. 18 into 2, 36 centimeter. Yeah. Please make sure that you give your minus sign convention in all the formulas so that your answer will be correct, answer will be neat, and you will get the exact answer. Okay. So your sign conventions are very important when doing the problems, both for spherical lenses and spherical mirrors. Okay. So I hope you're clear with the spherical lenses part. So with this, we are finishing the chapter. And for the next chapter, we'll see what what are the other properties of light. Here we saw only reflection and refraction. In the next chapter, we'll see what are the other properties such as dispersion, scattering, and then we have the eyes. So we'll see that in the next chapter, and thank you.